Today we are talking about work. All right. Well, let's start talking about it then. Work depends on two things, okay? The two things that work depends on are force and distance, okay? So basically, work is done when a force is applied and then that object moves in the distance that the force was applied. So our equation for this is going to be work equals force times distance, which we can just write as W equals FD. So that's our new equation, okay? Now, let's think about what the units might be for work. What are the units for force? Newtons. What are the units for distance? Meters. So what do you get when you put newtons and meters together? Newton meters. Okay. However, what we call Newton meters is a joule, which we just represent with an uppercase J. So our unit for work is joules. They put in so many joules of work. Okay? You guys ready for your first example? Okay. So this one might hit a little bit too close to home right now with everything going on in the world, but it's called heading to the ER. All right, so we have a nurse, okay? And they are pushing a gurney that has a person on it to the right, okay? So this person who's on the gurney has a mass of 72 kilograms, and the gurney has a mass of 15 kilograms. We are pushing on this with the force of we don't know yet, okay? Now, what we do know, though, is whatever force we're pushing at is creating an acceleration of 0.60 meters per second squared. And we want to know how much work this nurse is doing if they push this gurney a total of 2.5 meters. Now, seeing everything just slapped up here like this is sort of driving me insane. You guys know that I like to make a list of my known values, okay? So let's talk about what we know. We are going to be looking at this person and gurney together as one object, okay? It is our object. So if we were to do a free body diagram, both of those would be represented by the dot, okay? Now, if we're considering these one thing together, what is the mass? Is it 72? Is it 15? Is it some combination of the two? What do you think? It's a combination. What are we going to do with these two numbers? Yeah, we're going to add them. So what's 72 kilograms plus 15 kilograms? Good job. It's going to be 87 kilograms. Okay, so that's good. What is the distance that we're traveling? We're going to be going 2.5 meters. What is our acceleration? Yeah, 0.60 meters per second squared. Is there anything else that we know? No, not really, right? So that we can get a visual of this, how about we draw the free body diagram really quick, though? What forces are acting on this? Yeah, gravity, that's always a safe bet. What else? Yeah, we got some normal. We got one more. Yeah, the nurse. And what we're going to call the nurse is F with the subscript A for applied, because she's applying a force to the patient and the gurney together. Yes, sir.
Would there be any friction?
We do not have friction in this example.
Okay.
No friction in this example. So from here, I think we can solve for the work done by the nurse. We have our equation, right? We don't know what the work is. We're looking for that. Do we know what the force is? We can find it. How can we find it? Mass times acceleration. Perfect. And do we have the distance? Yes. Okay, so let's start by solving for that force, though. We're going to do mass times acceleration. So we're going to take that 87 kilograms and multiply it by 0.6 meters per second squared. So what is our force that the nurse is applying? 52 point what? Yeah, what are the units? Yep, newtons. Good job. Okay, so now to solve for work, we're going to want to take that force we just found of 52.2 newtons, and what are we going to multiply it by? What's our distance? 2.5 meters. 0.6 is the acceleration. Okay, so when we take 52.2 and multiply it by 2.5, what do we get? You say 130.5? I like the sound of that. What are the units on it, though? Joules. Good job. Okay. Now, question. If the intern doubles their force, but only goes half the distance, does that mean they apply more force, less force, or the same amount of force? Why?
Because you're basically equaling out the equation if you split one in half and double the other.
Exactly. So like think about it like if your force was 1 and your distance was 2. But then you double your force, so now it's 2 and your distance would be half, so it's 1. Either way, when you multiply those together, what do you get? You get the same thing, you get 2, right? So that's what's going on here. Okay, I'm going to erase this now, and we're going to draw out a scenario together that then you are going to try and solve. You guys think you can handle that? I think you can. Okay, so I call this example Darwinism because it takes place on the Galapagos Islands. You guys learned about that, right? Okay, so there's a species of finch that we have on the Galapagos Islands, all right? And it can exert a force of 205 newtons with its beak. Okay, that's a lot of force for a beak, huh? Yeah, it is. Okay, now it is trying to open up like a case and get to a seed because it's hungry. Now, it breaks the seed after it travels a total distance of 0.4 centimeters. What I want you to tell me is how much work did the finch's beak do? You can talk to a buddy if you feel the need to. Huh? Centi is 100, yes. There are 100 centimeters in a meter. Give it a go. We need to first and foremost convert this into meters. So we're going to take 0.4 centimeters, and in 1 meter, there's 100 centimeters, right? So what is the 0.4 centimeters in meters? You said 0.004? Okay, so now we're going to take that number And we're going to multiply it by this 205. And what does that give us? The 0.82 joules. So you guys just remember to convert and how we do the conversions, okay?
What happened? I moved the decimal place.
The wrong direction?
The wrong way.
All right, do you guys have any questions about this one? All right, well then let's keep going. Because there is more to learn about work. I know you're all so excited, right? Okay, so do you guys remember back when we were doing Newton's laws? And I just kept trying to move this desk, right? Did I ever succeed? No, I'm very weak. It's attached to the ground. And on top of that, it's freaking heavy. Okay, so my question for you is, if I am up here and I'm pushing on this desk, let's say I keep it up for like 30 minutes, an hour, I'm dripping sweat, it's not budging, I'm putting all of my might into it. Have I done work on it? Oh, what'd you say, Trunks? Yeah, it never moved. So no matter how fatigued I feel, no matter if I'm sweating so much, I went through my first shirt, I went through my blazer, it's dripping, I'm gross. Okay? I still have not done any work at all. Because sure, I applied a force, but it didn't move anywhere. So there was no work that took place. Now, in addition to that though, let's think about something else. One of your guys' favorite things. How do you think stuff is affected if maybe the force is coming in at an angle? Oh, I see those faces. Okay, so we apply forces at an angle, don't we, sometimes? So I'm going to make your guys' life so much easier. What we're going to say for work is that if there's an angle involved, that work is equal to force times distance cosine of whatever that theta is. Okay? That is our equation to use if we are applying a force at an angle. All right? So now we're going to do an example with that. If you guys feel like you need it, I mean, we're going to do it. I'm kidding. Don't worry. I don't have anything better to do with my time. I really don't. I know that's sad, but you know, it is what it is. Okay, so this one is called the gravity escape system. All right, so we've got this gravity escape system and it's enclosed. And enclosed in this, we have a lifeboat and we're trying to lower it down a ramp. So here's our ramp. And our ramp is going to be at, I believe, I want to make sure I get the angle right. Yes, it's at a 60-degree angle, okay? And we have a lifeboat that is going to be, this is even worse than the lifeboat I drew during my last class. It looks like a banana. It's a banana lifeboat. Even put a little top on it, okay? You got a banana lifeboat going down the ramp, all right? Now, this lifeboat has a mass of 4,900 kilograms, okay? It's a very heavy lifeboat. And it's going to end up overall traveling a distance of 5 meters. Okay, so this is all we have, and what we're asked to find is the work. So let's list out our known values. Okay, so we have the mass. What's the mass? 4,900 what? Kilograms, okay. We have the distance. What's the distance? 5 meters, okay. We have theta. What's theta? 60 degrees. Okay, and we have one other thing that's going to be important. What do you think? Let's look at this. What forces do we have acting on this ramp? Okay, we got gravity. There's still gravity there, though. Yeah, it's just called like gravity escape. It's trying to escape the gravity, but the gravity's there. And what's the one other thing we have acting on it? No, if I don't mention friction, there isn't friction. Normal. Okay, normal. So, I didn't mention a specific acceleration, did I? No. So what do you think the acceleration is? I heard the right answer and the wrong answer. It's going to be 9.8, okay? Now the reason we're not making it negative is, listen closely. Work is going to be positive here because gravity is pulling down and the ramp is moving down, which means they're working together, which means it's going to be positive, okay? So I'm just going to put G equals 9.8 meters per second squared, and we're trying to find work, okay? We're trying to find work. Now, we know that work is equal to what? Force times distance, okay? Well, we've got the distance. Do we have the force? No. Okay. Who remembers how we find force? Perfect. Mass times acceleration. Okay, what's our mass? 4,900 kilograms. And what's our acceleration? 9.8. 9.8 what? Yep, meters per second squared. Okay, so knowing that, what is our force here? For what? 48,020. What are the units? Newtons. So that is a lot of force. Okay. Now, since we know that and we know the distance, can we find the work done? Yes, we can. Okay, so to find work done, we're going to do this times what? What's our distance? 5 meters. Okay, so what is our final answer? Also, I want you guys to make sure that you're 100% positive about what you got as your force. Okay, good. I heard 480,020, and I put it up there, and nobody said anything, and I'm just like, that's not what I got. Okay, so that's what we got, right? Okay, good.
Answer is 240,100. Wait, 240.
We're forgetting something. What are we forgetting? You guys just told me to do that, but you left out one thing. This is at an angle, isn't it?
Yes.
So what did you guys forget to include? See? What's our theta? Okay, now, what is your answer? Is that what you guys said? Okay, what are the units? Joules. Okay, you guys, you've got to keep an eye out for that theta, right? You see how much it changes your answer? It changes it a lot, right? Okay. So I've got a question for you about this one. What if the lifeboat here, instead of just sliding straight down, it's going to slide halfway, get stuck on something, and then overcome that and keep sliding the rest of the way? So, is the work done the same, less than, or more than? Greater than sounds way better than that. Yeah, it's the same. Why is it the same? It still travels the same distance. It still has the same force, right? Okay. Awesome. Are you guys ready for one of these to try on your own now? What are we going to make sure we keep an eye out for? It starts with an A. Angle. Good job. Okay, so we have a parent pulling a child in a little red wagon. Okay, so here's the parent. Set on a hat to protect himself from, the sun. Skin cancer is real, you guys. Protect yourselves. Okay, and there's this little boy here, and he's having a good old time. He's having fun. Now, the father is pulling him at a constant speed, and he's pulling with a force of 16 newtons over a distance of 12 meters. Is there somebody at the door? Thank you. All right. Now, the handle of the wagon is inclined at an angle theta of 25 degrees. All right? We want to know how much work the parent is doing pulling this child. And I'll do one more thing for you guys. I'll draw you out a little free body diagram. What are all the forces we have acting on this kid? Okay, we got gravity. What else? Normal. And then we got one more thing. The dad. Remember, they're pulling with a tension force. Okay. Find the work done for me. When you think you have a number, feel free to holler it out. I'll shove it up on the board. We'll see how it goes. Huh? 174.01. Okay. Have any other guesses? Or is anybody who agrees with this? Somebody said they agree with it? Yeah? Don't worry. We'll walk through it, see if we get to the same place. Okay, from looking at some eyes, I think some people didn't get that. So let's go over what they did to get that answer. They said, all right, work is equal to force times distance cosine of whatever theta she gives me, okay? The force we were given is what? Yeah, 16 newtons. What's the distance we were told? 12 meters. And what's the angle we were given? Okay, so with that information, what do we get? Awesome. Good job, guys. Okay, any questions about this one? No? Don't worry. There's still more. Right? I know, you're so disappointed. Like, how dare I teach you physics in my physics class? Oh, what are they going to do with me? Okay. So we've seen how work can be positive, right? We've seen all positive work, correct? And we talked about how work can be 0, but what about negative? Do you think that work can be negative? Okay, so when work is positive, it's when it's sort of like moving with you, right? Okay, it's moving with the force that you're applying. What if there were some force in the universe that's pure and only intention was to oppose your movement? What would it be called? Friction. Isn't friction's only purpose to oppose your motion? It wants to stop you, okay? So if we have something like friction applied, do you think there's a chance that there could be some negative work there? Okay, so let's look at these then. So positive work. If this is the way the distance is going, if we're going to the right, which way should the force be pushing? To the right, right? If we're doing positive work. Okay, so that could be straight, or that could even just be, it has to go to the right in some way, all right? Some component of that vector needs to be pushing towards the right, okay? Now, what if this is the way of the distance, but 0 work is being done? Which way would the force possibly be pointing then? It's not going to point to the left, no. That would be negative work. It could be down. Could also be up. The key here is it's going to be perpendicular. To give you an example of this, because I know it's weird, right? Say I'm standing here holding this book, okay? Now, by keeping it in the air, am I doing work? No, it's not traveling anywhere, okay? Now, what if I do this? Did I do work on the book? No, I didn't. Because the force that I'm applying is the force that my hand's pushing up on this book. So if I only move left to right, I'm not applying the work. I'm not putting it in. Now, if I take this book and then I lift it, am I doing work? Okay, then I'm doing work. But if I'm just moving left to right with this book while applying this upward force, I'm not doing any work on the book. Okay?
So like distance doesn't matter.
Distance does matter, but the thing is that the distance that's getting applied to this isn't a force for me. Yeah. It's not a force that's on this book. All right. So what about negative work? So if this is our distance, which way would the force be pushing for negative work? Yeah, it'd either be completely to the left or it just has to come off to the left in some way. Okay? So this would be positive, 0, and negative. Now to test to see how much we really understand this, we are going to do a little activity up here on the board, okay? I'm going to erase these, and I'm going to draw 4 images up here, all right? Don't get ahead of yourself, though. So we've got 1, 2, 3, 4, okay? All of these are moving to the right. However, I'm going to show some different forces being represented on them, okay? This would be one of the forces. That's one of the forces. That's one of the forces. And that's one of the forces, okay? And we're going to call these A, B, C, and D. So what we need to do is look at these and organize them from the most work that's being done to the least work that's being done. And when we think about this, we need to think about it like a number line. So let's say that it's like 0 is in the middle. So all over here would be positive work, and over here we're going to make negative work, okay? So which one is doing the most work? Which one? D. Okay, why are we saying D? Okay, but what about C? Yeah, you guys are right. It's going to be D. Now, the reason it's D and not C is because you'll notice in D, all of that force is going that direction, right? In C, some of it's also in that vertical direction. It's not all horizontal. So that means C is going to be in which place? Is it going to be next? Yes, it's going to be next. Because it has some positive work being done on it, just not as much as D does. Okay, so which one's going to come next, A or B? A. Why is A next? Yeah, it's 0 work is being done. So that is like basically, if instead of trying to push this desk around, I was trying to push down on it, okay? When I try to push down on this desk, does it go any more into the ground than it already is? No, it's just still chilling here. I have not pushed it through the tile, into the ground, through to China, all right? It's not there. It's still here. Okay, so that means which one's last? Which one? B. Because B is going to be the most negative here because the force is to the left, but the distance is to the right. So who knows? Maybe that's some friction. Okay? Or maybe you and somebody else are pushing and the other person's stronger. I don't know. Okay? Any questions about this? No? All right. You guys are so smart. Do you feel smart right now? You should. You should feel smart. Okay, well, you got to start feeling smart soon because you know how you guys hate it when I mention vectors? Some of you at least. Now, we've already done some vectors, right? But something that I've noticed that people tend to dislike even more than me mentioning vectors is when I go, it's great that we've learned this, but you know what we can do with it? We can add multiple different works being applied together. We can sum it all up. Because remember when you guys thought like Newton's law, second law was like really easy, F equals ma, and then I was like, we've got to add them. Or when you thought vectors were easy, and then I was like, well, we can add them. And then you guys like glaze over and just get, That's what's going on again. Okay? So we are going to sum up different works. So what this looks like is we're going to say work total is equal to work 1 plus work 2 plus work 3, and so on and so forth to some n number of works. Okay?
What is TOT?
Total. So the total work. And I know for a fact you guys don't need an example with this, right? Like you're good. You're 100 on this. Okay. I know you're getting sick of that joke. I'm sorry. Let's do it, okay? This one's called jamming out. Because how else would have any of us gone through 2020? Seems like we're going to need it through 2021 too, am I right? Oh, God. Okay, so you and your buddies are about to start your band practice. However, you realize that the drum set needs to get moved over just a little bit. Stop falling asleep. I'm entertaining. Stop it. So I'm going to draw like the tiniest little drum set ever. It's just going to be like, one. This is a drum. Just take it for what it is, okay? It's a drum. Okay. And you are going to push the drum with your extremely long arms. Okay? Now, when you are pushing this drum set, you are exerting a force on it. So let's represent the drum set with a dot for this free body diagram, okay? You exert a force on it. So you are applying a force on it, and the force that you're applying to it is 24 newtons. Okay? However, your favorite thing in the world, kinetic friction, is going to be present, and it's going to be working against you. Okay? So the kinetic friction is going to be working against the drum set. And it's almost working as hard as you. It is going to be working, since it's to the left and it's against your movement, negative 22 newtons is what the kinetic friction is doing. Okay? And overall, by the end of this, the drum will have been moved 1.5 meters. What we need to know is the total work done on this. Now, there are two other forces acting on this drum set. What are they? Gravity and normal. Okay, so we need to take that into account because when we're totaling all of the different parts of work, and work is force times distance, we need to take into account all of the forces. So we'll have the work of the normal force, plus the work of the force of gravity, plus the work of that applied force, plus the work of the kinetic friction. Okay? Now, I have some really good news for you, though. What do you think it is? Yes, that normal and gravity will be 0. The work of the normal force, nada. The work of the gravity, we don't have it. All we have to deal with is this applied force and this kinetic friction. That's all we're concerned with, okay? So we now know that the total work is going to be equal to the work of that applied force plus the work of that kinetic friction. So we need to figure out what those are so we can add them together, right? Yeah? Okay, so let's start with the work of the applied force. If work is force times distance, what's our force? 24 newtons, good. And what's our distance? 1.5. Okay, so what is the work done by our applied force? 36 joules. Okay, so we got that one. Now we need to think about the work done by this kinetic friction. So what is the force of kinetic friction? Yeah, it's negative 22 newtons. Okay, and what's the distance? It's still going to be 1.5. Good job. So what does that make our work due to kinetic friction? Negative 33 joules. All right. Now here comes the hardest part of this entire problem. What is 36 minus 33? What? No, what's 36 minus 33, you guys? 3, right? And that's your answer. All right, question. Do you think that friction always does negative work? Yes, no?
Maybe.
Think about it. What did we just say the only point of friction is? To what motion? To what it? To oppose it, right? It's always going to work against whatever you're doing. So I ask you again, is friction always going to have negative work? Yes. Okay, cool. That means we are on to our last problem of the day. All right. Do you guys remember back when I made the joke that none of you guys really appreciated about passing the salt because my mom's bad cooking?
Yeah.
Okay, so now we're going to pass some coffee. Okay, we're going to slide it over, okay? Now, this coffee mug has a mass of 0.12 kilograms. And we are going to slide it a massive distance of 0.15 meters. Using an even bigger force of 0.10 newtons. There's so much acting on it, okay? Now, one of the most important pieces of information I have for you here is that the coefficient of kinetic friction between the mug and the table is 0.05, okay? So let's draw the free body diagram together for this. What all do we have acting on this mug? Gravity, good. What else? Normal, okay. What else? Yep, the force applied. What else? Kinetic friction, good job. Okay. We want to know how much work is done on this mug. Now, I'm going to give you guys one more piece of information. But there's only one way this is different from the problem we just did. And that's that you're given a coefficient of friction instead of the straightforward force of friction. But do you guys remember what friction is? I said it all the time. I was like, friction is fun. Yeah. Okay? So you find the force of friction by taking that coefficient of kinetic friction and multiplying it by the normal force. You guys have everything you need to find the normal force.
What is that? Is that an N or a U or what?
It's mu. Mu K is the coefficient of kinetic friction.
So it's a special.
It's a Greek letter, yeah. All right, try and figure it out. When you think you have an answer, let me know.
I got it. Is it 0.897?
I don't know, but I'll put it up here. Is this the time in the show where I need to show you how to do it? Okay, sit back, take this all in. Okay, the first thing I like to do is clean everything up by listing out my knowns. So I'm going to put that my mass is 0.12 kilograms. I'm going to put that my distance is 0.15 meters. That my coefficient of kinetic friction is 0.05. And that my applied force is 0.10 newtons. Okay, now that I have that, I'm going to think about what I need to find, which is my total work being done. So I'm going to say work total is equal to the sum of all of this work. So the work of the normal, the work of the force of gravity, the work of the applied force, and the work of the kinetic friction. Then I'm going to be like, I want to make this easier on myself. What's equal to 0? Normal and gravity. They're not really doing any work. They're not causing anything to move. So once I get here, I'm like, okay, so to find the total work, it's going to be the work of the applied force plus the work of the kinetic friction. So I might feel uneasy about finding the work of the kinetic friction right away. So I'm just going to focus on this applied force, okay? So I'm going to say, the work of the applied force. I know that work is force times distance. What is my applied force? What is it? It's 0.1, right? 0.10 newtons. Okay, that's my force. What's my distance? Yeah. 0.15 meters. Okay, so what is my work of the applied force? Did you guys say 0.015? Everybody agree with that? What are the units? Joules, okay? Now I have to deal with the elephant in the room. I have to deal with this work due to kinetic friction, which is going to be the force of my kinetic friction times the distance, right? Because this is just another way to write force, because it's for the kinetic friction specifically. So I need to focus on finding this. Well, in order to find that, I have to do my coefficient of kinetic friction times the normal force. What's my coefficient of kinetic friction? Yeah. Okay. It's 0.05, right? Now, normal is not 0. There's no work done due to the normal. How do we find the normal force? Mass, right? Yeah. It's the same way you find gravity. You would take the mass of the mug, which is 0.12 kilograms, and you would multiply it by 9.8 meters per second squared. Okay? Now, what does that give us? It's what? 0.05 what?
88.
Yeah, this is a do-it-yourself problem, you guys. I'm not going to stop you on mistakes on these. I'm going to take your word and go with it. If you look at the notes I've posted, I didn't solve this problem. This is for you to solve. Okay? So you have that. That means you need to solve for the work due to kinetic friction, right? So that means you're going to take the negative 0.0588 newtons and you're going to multiply it by your distance. What's your distance? Okay, so what do you get when you do that? Negative 0.008 what? Okay. So that means you're going to do 0.015 minus 0.00882. What do you get?
Zero, zero, 618.
Is that what everybody got?
Yeah.
Yes. Okay. And you're done for the day.